our graphs, we vaguely talked about like real world situations, but we didn't actually look at the equations that go with them. We just said like, hey, let's pretend that this equation is what models our data. Now we're actually going to look at the actual equations that model our different types of data. Okay, so these are the 5 main models, which remember a model is just an equation that represents something. Okay, you do not have to have these memorized. Okay, if I asked you to use it on a test, I would give it to you. All right, the only thing is though is that you do need to know like which situations would use which models. Does that make sense? So we've talked about our first 2 in depth now. Okay, so what would a situation be that would do exponential growth? Probably not population. So bacteria growth would be a good one. Or like COVID cases in the first few months, right? Both of those would work. Now, what would be an example of our exponential decay? So like polar bear population, right? Deforestation. We all with me? Yeah. Now, our next ones we haven't seen before. Okay, that third one is called our Gaussian model. Okay, and you might not have heard the word before, but you might have actually seen our graph before. So, this is what your basic Gaussian model graph looks like. Basically, I let my variables be 1 and 0. Okay, can anyone tell me what kind of graph that is? What? What type of curve? It's used in statistics. It's our normal curve or normal distribution. So basically, like a big example would be like grades. So most people are going to say that the things that are really low or the things that are really high, you're not going to have as many of those. So like you're not going to have as many, hopefully, people that make D's and F's. And you're not going to have as many people that make 100s, but you'll have more people that make C's, B's, and low A's. Does that make sense? So that's where it, like you have lesser things on the ends, more stuff in the middle. Okay? So that's one example. There's lots of examples that use your normal distribution. We're not going to go over that one a ton, just because if you continue on into statistics, you'll see it there. So we're not going to reference it as much. Now, our next one we are going to talk about, which that's our logistic growth model. Okay, so notice that it takes on a very similar form to our exponential growth model, but notice that it's now been put into a fraction. So let's think about, with our exponential growth model, right, it continues going up forever. Agreed? Does that make sense when we're talking about real-world population? No. Not really, right? Because if I'm talking about like rabbits, say like in the zoo, would it make sense that they would just keep growing population forever? No. What's eventually going to happen?
The universe is going to die.
Well, some of them will die. What else?
They'll run out of resources.
Yeah, they'll run out of resources. Space, food. If you're in the wild, you would have natural predators, things like that, right? Or even if you're talking about sales of like an iPhone, right? Does it make sense that the sales would continue to increase forever? No, eventually they're going to level off, right? Because it's not as exciting anymore. People get tired of it, that sort of thing. So what makes more sense in the real world is something that looks like an exponential growth model, but then eventually it levels off. Okay, and that is our logistic growth model. So again, we said some things would be like population with a limiting factor. So like space, food, things like that. And then our last two are our logarithmic models, and we've seen natural logs and common logs before. So again, remember, you don't have to memorize these, but we will have to know how to use them. You all with me? Look at an example. Okay. Alright, so here we are looking at the amount of money in billions, okay, that has been spent on mobile advertising. So it tells us the amount S in billions of dollars spent in the United States on mobile online advertising in the years 2010 through 2014 are shown in the table. A scatter plot of the data is shown below. And then it gives you your table and your data. Just by looking at the data, what type of pattern does it look like?
Exponential growth.
Exponential growth, which is why they give us an exponential growth model. Now, it does limit us only between 10 to 14. And that's because after that point, that model is not going to be as accurate. Okay, you would need a new model. And then it says where T represents the year, with T equals 10 corresponding to 2010. The first part asks us to compare the values using the model with the amounts shown in the table. And then, according to this model, in what year will the amount spent on mobile online advertising be approximately $65 billion? So the first part is asking us to compare values. So this would be our actual values. They're asking us to look at what our model values would give us. So what are our X values in this case? Year. So remember, we have two types of variables. They are independent and dependent. Your X variable is going to be which one of those? Independent. And time, if it involves time, is always going to be independent. Okay? So this time, our T, or our time, is what's acting as our X values. Okay? And then our Y values is our amount of spending. So if I wanted to see what numbers we get from the model for 2010, 2011, 12, 13, 14, what would I do?
Plug in the year for T.
Yeah, plug in the year for T, and you're going to get a decimal approximation. So let's get out a handy dandy calculator. Now, when I'm plugging in my time values, are we going to plug in 2010? No, what are we going to plug in? Basically, the last two, because notice that it says T equals 10 corresponds to 2010. And that's really common when we're looking at these application models, is that they're going to give you some sort of unit conversion. Because most of the time we don't want to plug in the entire amount, because it gives us rather large numbers. So when we plug in 10 into this, so you have 0.00036 times e to the 0.7563 t, what do we get? Anyone get an answer?
0.697.
So 0.69. Okay. Now remember that you can just do second enter or scroll back up if you're on the scientific. So that way you can now type in 11 instead. And what do we get for that one?
1.47. 1.48.
Okay, 1.48. What about when we plug in 12?
3.15.
What is it?
2.15.
1.5. Okay. 13.
6.7.
And 14.
14.28.
So, were we all able to get those numbers with whatever calculator we're using? Are those numbers relatively close to what we had for our actual data? If so, as we go farther, what happens to the error?
It increases.
It increases, it gets bigger, which makes sense because we're dealing with an exponential function, right? So the farther out you go, the larger your error is going to be, right? Now, what's it asking us to find on the second part? So what year is the advertising 65 billion? So what are we wanting to do? What are you trying to solve for?
T.
T. So that means they have to give us
S.
an S. Do they give us an S? Mm-hmm. Do I want to plug in 65 billion? That would be a rather large number. Well, I hope not. What do we want to plug in instead? 65. So do we all say that our S is in billions of dollars? So this is 65 billion. Then we would just plug in 65. And then what are we doing? Yeah, we're solving for T, right? Now, our numbers aren't as nice as the equations that we've been dealing with, but the process is still the same, okay? So what's our first step for our exponentials? Well, like in general, what is it?
Oh,
Isolate your exponential. So yes, you would need to divide. Now be careful, because again, we vaguely talked about this. We said that we don't want to approximate too early, because that's going to increase your rounding error. Now we are going to have to round this answer, because it's going to be a long decimal, but we want to do that at the very end. So we're going to leave it like that right now. So then what's our next step? How do I get rid of the exponential?
Find the natural log.
Take the natural log of both sides. So when I do that to the left side, I get the natural log of 65 divided by 0.00036. And then what's going to happen on the right side when I take the natural log?
It's going to cancel the E.
It's going to reduce with my E. So we're just left with what's in our exponent. So then what's our last step? Divide. So we get the natural log of 65 divided by 0.0036, all divided by 0. I don't know why. 7563, and that equals T. So again, we plug all of that into our handy dandy calculator. What do we get?
62.004.
Okay. So that is our mathy answer, right? But we have to make it make sense in context with our application. What does it ask us to find?
The year.
The year. Does 16.004 make sense as a year? No, but if we refer back to what it tells us that our numbers correspond to, right? Basically, we're talking about years after 2010. So I would have 2016. Agreed? Okay with that? Alright. So let's look at our next example. So it says in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? So, it tells us that it's increasing according to the law of exponential growth. Basically, that's just a fancy way of saying we can use our exponential growth model. So again, remember, I would give this to you. So we have a times e to the bt. Agreed? So what are we looking for this time? What did it ask us to find? How many flies there will be after 5 days. So what are we going to want to do?
Make T5.
Yeah, but what's the problem if we did that right now? We don't know what A and B are, right? We all with me? Now, we don't have an equation to plug into, because if I plug in 5, we would just have A equals 5B, which doesn't help us a whole lot. So what do we have to find? Nope. A and B, right? Are we all with me? So that's where that other information comes into play, okay? Again, what is our T representing in this case? Days, which is time, right? So if they give me a set of numbers, notice that we could plug that in for T, time, and Y, which is going to be our population. So we would have 100 equals A times E to the 2B. Agree? Now, what would my other set of information give me? 300 equals A times E to the 4B. Now, on either one of those equations by themselves, can we solve for A and B? No. But if we have two equations with two variables, what do we have? A system of equations. Can we solve a system of equations? Yeah. It has e's in it, but that's okay. It doesn't change anything. What are our options for solving a system? Like, what are your methods? Substitution. Elimination. Graphing. And matrices. Okay? We probably don't want to use graphing or matrices on these because it's not going to turn out very pretty. Okay? Technically, we could do elimination. It's just not going to be very pretty because we have things that have e's in them. Alright, so the easiest method in this case is going to be to use substitution. Are we all with me? Okay. Because notice on either one of those, A is pretty easy to solve for. What do I get if I solve for A on this first one? So I want to get A by itself. So what would we do? Well, yeah, but I'm going to use this one. So there you go. So A equals 100 over E to the 2B. Agreed? So once we have one of our variables solved for, what's our goal? Plug it into the other one. Okay, remember you have to be careful about that. So now I'm going to plug that back in to my other equation. So we would get 300 equals 100 divided by E to the 2B times E to the 4B. Now, is this E to the 4B technically on top of my fraction? Yes. What is it technically over? 1. Right? So I can reduce things. Yes? If I have E to the 4B divided by E to the 2B, Well, they have the same base. So what do we do to our exponents? Subtract them. So 4b minus 2b gives us 2b. Or not 2b. So we end up with that. Which, from there, it's basically like any of the other equations that we've been dealing with. Agreed? So what do we want to do? What's our first step? Isolate your exponential. So what do we need to do first? Divide by 100. So we get that 3 equals e to the 2b. So then what do we want to do? Take the natural log of both sides. So we would get that the natural log of 3. And when I do that, this is the right side, notice that my e would reduce. So we're just left with 2b. Natural log of 3 equals b. Agreed? Yes, no, maybe. Okay, now, once I have b, what's our goal? To find what? A. Are we all with me? I have b. We had 2 variables that we needed to solve for. So we still have to plug back in our b value to get our a value. Agreed? Yes. So I'm going to plug this in now to there. So I have 100 divided by e to the 2 times 1/2 natural log of 3. Well, what is 2 times 1/2? 1. And then what is e to the natural log of 3? 3. So we just end up with 100 divided by 3. Now, remember, we said our goal was to leave our variables as exact for as long as possible. Well, now we do need to round them. Because when we make our equation, we need to have decimal approximations for our a and our b value. So what is a going to be approximately? 33.333. And what would our b value be approximately? Five, 4, 9. So we have 33.333 times e to the 0.5498. Now, if I just ask you, like, hey, give me an equation that models this data, that's what your answer would be. But they ask us to go a step further. What are they wanting us to do? Find it after 5 days. So again, what did we say we're going to do with that 5? Plug it in for t. And again, you would just plug all of that into your calculator. You're going to use your calculator a lot in this section. So what do we get that y is approximately? It's a lot. A lot of fun. What do we get?
I have 108.8152.
You said 108? Did anyone else get 518?
Yeah.
Okay. So we said 518 point what? Now, again, that is our mathy answer, right? Does that answer make sense in context for what we've been doing? You're not gonna have a fraction of a fly unless you like killed half of one or something. Okay? So how many flies do we actually have? 18. So for the most part, when we're dealing with population, you're going to round down. Because, again, you can't round up of a fly or a person or an animal. Now, I would not count it wrong if you said 519, but just so you know, like, that's what we would actually do. Question?
What did you do once you plugged the
Which one?
when you plugged the answer into the first system of equating the second one?
This answer, when I plugged in B back in to find A? Is that what you're asking? Or when I plugged in what we solved for A to get to here?
The second one, I think.
This one?
Yeah.
So notice that I have A equals 100 divided by E to the 2B. So that's what I put in for A.
Right, I get that.
'Kay,
But
well then-
how did you find B?
Thank you. I'm just solving. So notice that E to the 4B divided by E to the 2B, right? Just like if I had X to the 4th divided by X squared, right? We subtract our exponents.
Okay.
So 4B minus 2B, because I'm subtracting my exponents, gives me 2B.
Okay.
And then we just have a 100 in front.
Okay.
And then from there, it's very similar to what we did yesterday. So we have to get our E to the stuff by itself. So we divide by 100.
Okay.
And then we take the natural log of both sides. And then divide by 2.
I get it from there.
Gotcha. Other questions?
Whenever you have A equals 100 over E to B.
Yep.
And then you have E squared times 1/2.
Yeah.
How do you take inverse E natural log of X?
This one? Well, what is 2 times 1/2? 1. And then E to the natural log of anything, right? It's just going to be whatever's on the inside. So we just get 3 there. Other questions? Alright. Let's look at another example. We might have seen examples like this before in some of our science classes. It's on carbon dating. So carbon dating uses an exponential decay model, specifically that one. R equals 1 divided by 10 to the 12th times E to the negative T divided by 8,223. It's a negative because it's decaying, okay? And that's because that's the amount of carbon that is in an item. So if you discovered a fossil or something like that, or rock, things like that, you can use this exponential or decay model to determine the age. So they specifically tell us to estimate the age of a newly discovered fossil that has the ratio of carbon 14 to carbon 12 as R equals 1 divided by 10 to the 13. So what are we solving for? What variable?
T.
What are we solving for? What's it ask us to estimate?
The age.
The age. Well, what is age?
T. Wait, R.
Age is going to be, I was saying, no, that. T, right? Because age is time. It's how much time has passed. So it's going to be our T value. So that means that what do we have to do in order to be able to solve for T?
Find R.
Plug something in for R, right? Do they give us something to plug in for R?
1 over 10 to the 13.
Yeah, so we're just going to plug that in and then treat it like any of our other exponential equations. So what's our first goal when we are solving exponentials? Isolate your exponential. So what do we have right now in front? Fraction. Which is technically the same as dividing by something, right? So how would I undo that? Multiply by 10 to the 12th. So if I multiply by 10 to the 12th, both sides. That'll reduce with my right side. Okay? But what is 1 over 10 to the 13th times 10 to the 12th?
20.
Yes, you would have 10 to the 12th divided by 10 to the 13th. Not quite. 1 over 10. Because notice that 12 of these would reduce and I would be left with 1 of those. Yes? So I have 1/10 on the left side. Well, now is my exponential by itself? Yeah. What's being raised to the power is by itself. I still have stuff in my power, but we can't take care of that until it's out of the power. Yes? So how do we get it out of the power? Take our natural log. And again, if I take the natural log of e, it's going to reduce. So then what's our last step to solve for t? Almost. What kind of 8? 8,223. Negative 8,223. You have a negative in front, so we need to get rid of that negative. So we'd have to multiply by a negative. And I just did it all in one step, that way I don't have to write more stuff. So then again, we will plug all of that into our handy dandy calculator. It's going to be a rather large number. We're talking about a fossil, so that's okay. What do we get? Yes, I need you to plug in your calculator.
How I go 1,800.
18,034.
934. Oh wait. Yeah.
167.
7.
I got 157. I'll make.
Yeah. Oh yeah. 157.
157.
Yeah.
And what's my unit?
Years.
Years. I'm talking about age, so that's the amount of years that it is old. Now for this one, because we're talking about years, like you can leave the decimal there, because that just means like that would be a couple months in, right? But when you're talking about like population of something, you don't want to leave point something of a person or animal or fly or whatever. Okay? Questions on that? Yes, no? Maybe? Okay. Alright. Do we need to write something down? Alright. So we're going to skip this one for a second and come back. We're going to look at our logarithmic model first. It says on the Richter scale, so how many of us have heard of the Richter scale before? Hopefully so. It is. It's the magnitude of earthquake intensity. So the magnitude R of an earthquake intensity I is given by R equals log of I divided by I naught, where I naught, or the initial I, is 1, is the minimum intensity used for comparison. Intensity is a measure of wave energy of an earthquake. So if any of y'all have ever seen like the movies where they have like the little like thingy that like moves up and down as the earthquake happens, right? That's measuring how many wavelengths are happening in a certain amount of time, and that's how they measure intensity. Okay? So it says find the intensity of each of the earthquakes. So what value did it give us already? I sub 0, right? They said that that's 1. So what does our R actually equal if this is 1?
Log of I, or log of I.
Yeah, log of I over 1, which is just really log of I. So that's really the equation that we're going to be using. And so again, this time, they give us an R value. So where do we want to plug that in? Into the R. And what are we solving for? I. So what would we do in order to solve for I?
10 to the log I, 10 to the 4th.
Correct. We're going to exponentiate with a power of 10. If I do that, what's going to happen on the right side?
Log I.
It reduces. So what do we get for I?
10,000.
A lot of them. One with a lot of zeros.
So how many zeros?
I don't know. Wait. 4 extra zeros from 10.
So how many zeros total?
5.
Oh.
100,000. There we go.
Do we agree?
Yeah. Close enough.
I don't know, that's what I'm asking.
10,000.
10 to the fourth is 10,000.
It's from the.
I'm missing.
You plug into your calculator?
Yes.
Okay,
It's 10,000.
there we go. That many. Alright, and again, that's measured in intensity, so we would just say, we don't have to put a unit on it, because it kind of doesn't have a unit, it's just measuring the intensity. Alright, so now, if we wanted to look at a 7.8, what would we do there? Same thing, but we're just plugging in 7.8 this time. So we would get that I equals 10 to the 7.8. So what do we get? Hold on. I need one person. What is it, Nate? Nate, read it to me.
63,095,734.45.
You said 95,000.
Yes.
And then what?
734.45.
0.45?
Yes.
Which is why this grows exponentially, right? So just plugging in a number that's a little bit bigger is going to give us an intensity that is exponentially larger. That is pretty big. Are we all alright with that? Yep.
How many decimal places do we always
If it doesn't specify, usually I like 3. If it does specify, then whatever it specifies to. Alright, we're going to go ahead and stop there today. Tomorrow, we'll be doing our lab, and our lab is going to be over logistic growth. So we'll look at the last example before we do our lab.